Okay, so here's section 8.4, and it's about roots of complex numbers, which is complex numbers, it's just the i's, right? But basically that means it ends up being roots of trig numbers as well, right? Because we can write these in trig form, and sometimes trig form is easy to deal with, like when we're taking powers. So kind of like de Moivre's theorem from section 8.3, but basically 8.4 is going to be the opposite of de Moivre's theorem, okay? And that kind of seems weird. You might be like, what do you mean by that? So here is what I mean by that. One thing you have to remember is that if you're taking a root, right, a square root is the same thing as a 1/2 power, right? We kind of learned that in algebra. Or a cube root, right, is the same thing as a 1/3 power. What I kind of both like and dislike about this section is literally all of the problems in section 8.4 are going to be asking you to do the exact same thing, but they are asked in a different way. So that's very annoying. But essentially what it comes down to, all right, so let's start with one of the very beginning ones, like why not number 1? Looks good, right? It's in long form, but it wants you to take the square roots of 4 cis 30, right? It's got it written in long form, but 4 cis 30. Now, square roots is a 1/2 power, all right? So it's like de Moivre's theorem. And so what's weird is it's not quite the opposite of de Moivre's theorem. It really is the same as de Moivre's theorem. Maybe I should put it's de Moivre's theorem with an addition, I guess I should say, to the theorem. All right, because you still do actually do 4 to the 1/2 power, right? Which is a root, so the square root of 4 is 2, all right? And you actually still do take 30 times a half, right? So when we're doing de Moivre's theorem, we take this to that power, and we take this times that. So that's 15 degrees. Now here is where the additional part comes in. Whenever you take a square root in math, right, if we're doing x squared equals 9, when we square root that, it would be x equals plus or minus 3, right? There's always however many answers there are, all right? And so if we're taking a square root, there's actually more than one answer. So here's what you need to do. You need to get as many answers as the root that you're taking. So if you're taking a square root, then you need 2 answers, right? And how you get 2 answers is the 2 stays the same and the cis stays the same. But we need to find the other degree. Well, the other degree comes from taking 360, because that's a whole circle, and taking that times the half as well, which is 180, and adding 180 to that, right, which is 195. And if we needed another third answer, we'd actually add that again. All right, but we only need 2 in this case, and I will go over that part again. All right, but basically you take 360 times the power as well, get 180, and that's what you add to it. But for instance, number 1 says, find the 2 square roots for the complex numbers. Leave your answers in trig form. So our answers are in trig form, great. And then it says, in each case, graph the 2 roots. So to finish this one, if we wanted to graph the 2 roots, I would just go to 15 degrees, which is really close here, and just go out 2. So I'd be like, boom, here's 1. And I guess it doesn't even want this. A lot of times on these I draw the line though, so you can see kind of what's going on. 195 is actually 15 past this, so it goes this way. So these are 2 answers right there. So it's like de Moivre's theorem. You still take this to the power of that, and you still take this times a half, but you have to get as many answers as there are. All right. So let's do like number 7. Why not? So it's going to be the exact same thing, but we start in a different place, okay? And they want us to not end. They don't want us to graph at the end. They want us to turn them in standard form at the end. So let's see if we can do that too. But it's going to be like all the homework is going to be the same thing. But it's just going to be a matter of your starting and ending spot. So number 7 says 2 plus 2i root 3. And again, it wants square roots. So we're going to take this to the 1/2. And if you notice, there is no good way. You can't even FOIL that. There's no good way to do this except for using trig numbers, all right? Because you guys don't actually know how to take roots of i's. It actually is just the worst thing ever. And I would prefer to do it this way, actually. So if we write this in cis form, I'm going to go, we go over 2 and up to root 3. And we can do the Pythagorean theorem again, right? Do 2 squared plus 2 root 3 squared equals c squared. I just think this is easier because I see, oh, 2 and 2 root 3 is 4, and that's 60. But if you didn't know that, then you could just do 4. 4 times 3 is 12 equals c squared. 16 equals c squared. Square root, get 4. And then you can do tan inverse of 2 root 3 over 2, and you get 60, right? So we'd end up at 4 cis 60. And then we got to take this, though, to the 1/2 power because we're going to do square roots. So square root of that, 4 to the 1/2 is 2. 60 times 1/2 is 30. So that's one of our answers, but we need another answer because we took a square root. So we're going to have 2 answers. So 4 to the 1/2 is still 2. Now how you get the other one is you take 360 times 1/2 and get 180 again, and do 30 plus 180 is 210. So I know that those were both square roots. So we'll do a cube root next so you can kind of see what that looks like. Yeah, and I think you're going to catch on as we do that. And then maybe we'll do number 27, so you can, or number 16 and 26. So you can see one that's not nice, 30, 60, 90, and you can see a cube root, and then you can see a 4th root as well. So, let's see here. Then it wants you to turn these back into standard form is what I want you to do on this one at the end. So that's where I go, oh, if I would draw it, I would be right here at 30 degrees, and I'd have a 2, but I actually am like, oh, 30-degree triangle with a hypotenuse of 2, this is just 1 root 3, right? So standard form is root 3 plus 1i, right? Now instead of doing it this way, let's do this, like if you're liking the drawing way, go ahead and draw it, but the other way to do this is just to write it long form, right? 2 cosine 210 plus I sine 210, and then use your unit circle. Cosine of 210 is negative root 3 over 2, and sine of 210 is 1/2. And if I distribute that 2, I'm going to get negative root 3, and then I'm going to get plus I. So those two things are your square roots of that, believe it or not. Which it looks like in this case you could just take 1/2 times those, but that does not always work. Okay, so be careful. I think it's just because it was a 30 and a 60, and it was nice. So that's what we're doing. So let's do a cube root and a 4th root, and then I think you'll have the idea on how to do these things. So, but again, they're all going to look like somewhat of a different setup, and you're going to go from there. So like on the next section when it says take cube roots, some of them start as trig numbers, and you're ready to go. Some of them start in standard form, and you got to turn them into trig numbers. But 16, it starts as trig form, but I'm going to condense it into the short form. And then it says cube roots. So if it says cube roots, that means we're going to have 3 answers this time. So you just got to be careful with that. So 27 to the 1/3 is actually 3, right, because it's a cube root. And then cis, and then 303 times 1/3 is 101. So that's nice. So this is not a 3069 or anything, but since I don't have to go to standard form, this isn't that bad. So here's the thing. There's this answer, but I need 2 more, because whenever you take a cube root, you need 3 answers. All right? So what I do is I take 360, whole circle, times 1/3. 1/3 of 360 is 120, right? So I do 3 cis. 120 plus 101 is 221, right? Yeah. And then 221, I add the 120 again, okay, to this. So 221 plus 120 is 341. Now, if you got confused and you're like, I'm just going to keep adding, well, 341 plus 120 is 461. But 461 is over 360, and cis can only be in between 0 and 360, and if you subtract the 360, you get back to 101, and you'd realize you were back to that answer, and so you would only have those 3 answers anyway. It's kind of like when we were doing the solving stuff, and you could keep going around and around, but we only need like 1 time around the circle. And this one says you can leave it in trig form. That's what's nice about those. Now, on 26, when it says solve, it's going to want it in standard form, I think. 27 through 32 are where it says you can do whatever you want with them. So, all right, one more. And then, dude, you're at the end of trig. You've learned everything that I need to teach you, which is probably a good feeling, since you're having to do it at home, and that's no fun. So, here's an equation. It wants you to solve it. But we are, again, going to solve it using trig. Alright? And here's why. We would subtract 81. X to the fourth would equal negative 81. Alright? And then we'd take this to the 1/4 power. And I'll tell you kind of using algebra why this will turn out the way it is. But basically we need to do negative 81 to the 1/4. But we actually need to put this in trig form first. Which might be a little confusing because you might be like, well, the 4th root of 81 is 3, so maybe we're going to have like 3i. So we can talk about that in a second. But trig form of this, negative 81 is actually just over here 81. Right? Because it's got 0 i's on it. So this actually is 81 cis 180. Right? Because in cis form, you can't have negatives. Right? You got to make sure you're in between 0 and 360. And this cannot be negative. If it was negative, you'd have to kind of like adjust for it by being like, oh. Like, so negative 81 cis 0 is technically the same as this, but we don't write any negatives in cis form. So that's why that's false. So you got to be over here at 81 cis 180, and now you can take it to the 1/4 power. And how do we take it to the 1/4 power? Well, this is the 4th root is 3. I guess 3 times 3 times 3 times 3 is 81. And then you take 1/4 times 180, which is 45. Yes. And then, alright, what we do is we say, okay, I need 4 answers. Hope I don't run out. Maybe I should put 2 of them over here. I'll do that. Then I'm sure I don't run out of room here. So all of them are going to have 3 cis on them. And now I take 360 times a 4th, which is 90. And I just keep adding 90 to this till I get all of them. So 45 plus 90 is 135. 135 plus 90 is 225. 225 plus 90 is 315. Now, I'm not going to lie to you. I would actually much prefer to leave these in trig form. I would honestly have to check the back of the book and see what they want. Maybe I'll just do that really quick. But I want to show you where they come from and what they would be, so we might still change them to standard form. What number was this? Let me write down 26. Yeah, they do turn them into standard form. That's what I thought. Once we have one of them, though, we'll probably be able to figure it out. So 3 cis 45 would be 3 here, and then a 45-degree triangle. So it's not like it's like 3, 3, 3 root 2. To find this, I'd actually probably set up an old school ratio of 1, 1 root 2, right? And do root 2 over 3 equals 1 over x, and these will both be the same. So you have root 2x equals 3 divided by root 2. So that's going to be 3 over root 2, or 3 root 2 over 2. Yeah. So this would be 3 root 2 over 2, and this would be 3 root 2 over 2. So this in standard form is 3 root 2 over 2 plus 3 root 2 over 2i, right? That's what that is in standard form. And honestly, these are all 45-degree triangles, right? So it's all going to be 3 root 2 over 2. It's just a matter of negatives, right? This one is going to be negative first. So it'll be negative 3 root 2 over 2 plus 3 root 2 over 2i. This one is going to be both negative, so negative 3 root 2 over 2 minus 3 root 2 over 2i. And this one's going to be 3 root 2 positive minus 3 root 2 over 2i. So those are actually your answers to this problem, are these. Now, where does that come from? Why is that important? Let me come back to some stuff that we don't do in Algebra 2, but you technically could do this in Algebra, just in case you're curious on how this works. Technically, this is factorable, but only with imaginary numbers. Because if I went ahead and did this, then I would be like, okay, x squared times x squared is x to the fourth. These are going to cancel, and then I'm going to have negative 81i squared. So the I squared is going to go away and get this. So I actually know that happens to factor into that. And then if you were actually to go, trying to think how this would factor x. Yeah, this gets, I don't even know if I could factor this, but if we went to go take square roots of these, we'd actually have to go back and take square roots of these, and we'd end up in the exact same place. Well, this one would just be x. No, because they've got an I in there, and taking square roots of i's again gets nasty, gets you down to here. So it is really interesting though, but like we learned that this had 4 answers, but the only way we'd be able to find them actually is using trig form. So I never gave you one of those in Algebra 2 because that would have been super crazy. So I think that explains everything. If it doesn't, let me know. But I think that's the plan. And that is section 8.4. So maybe work on those 2 over the weekend, get them to me by Monday. And if you send them over the weekend, that's totally fine too. I might have time to grade them. And then we can get you and Glenn your quizzes next week. All right. Sweet. Let me know if you got any questions.